Okay, so basically now, uh, okay, drawings for the steel project. Okay, I'm going to show you a couple of examples. Okay, uh, first of all, is this clear to everybody what I'm showing you right here?
Yes.
Yeah.
Okay, guys. Anyways, I sent you a folder this morning, and this is one of the drawings you have in the folder. Okay. And basically, don't go by this project because this project was slightly different. If you see here, you got 52.5, the length of the building, and this was a slightly bigger building. The same, in other words, the same configuration almost, but different dimensions. Now, of course, here, of course, you have your axes, you have your dimensions, you have your columns. In other words, you have your wind columns and all that. We will be designing all of these, so you'll be able to, you know, put the designation of the columns. The only thing that you haven't seen here, okay, is that normally when you're doing a roof plan, the architect needs to drain his roof, okay? Now, the architect can either use sloped insulation to create the slopes, or he can ask you to create the slopes, okay? So basically, you'd have to discuss it with the architect where, like, how big of a basin he wants to create. In other words, where does he want to slope to? Okay, and between you and the architect, you'll decide that okay, we'll put a roof drain here, and we'll put a roof drain there, and then of course the mechanical engineer, he's going to calculate based on the size of the roof, what's the size of the drain and the pipe. So the mechanical engineer gets involved afterwards, and so on and so on. Okay, now what you're going to have to do is, for example, you're going to have to make sure that your steel is adjusted so that it can create the slopes. Now, when you're creating on a roof, okay, the minimum slope that a roof should have in order for it to drain properly, the minimum slope is 2%, okay? That's the minimum slope. So that's what you should give on your roof. Now, so what you do is, for example, if this here is where I want, let's take this one, for example. So let's say I want to put a roof drain right there, okay? I'm going to put a roof drain right there. Okay. Therefore, I would have to take the furthest distance away from that drain. It's either going to be this one here or that one there, whatever one. I take the furthest distance, right? And then I multiply it by 0.02. And that means that all the steel around that drain has to be that much lower so that I can create that slope. And the way that we indicate that in structural steel is that, for example, here we said that our top of steel is at elevation 6,000. In other words, it's 6 meters above ground. So in other words, that would be what we would call all the flanges, all the whatever it is, would have to be at, they'll construct so that all the steel is at 6,000. By the time you put your steel deck on, everything should be at an elevation of 6,000 millimeters above grade. That's what we mean. Now, what happens here is that, well, let's start with the simple ones. Okay, so here, for example, this perimeter beam here, the top flange of that perimeter beam, the top flange of that perimeter beam, and so on, all the perimeter beams here on this side, these would all be set to the top flange at 6,000. Now, these perimeter beams here would be set a little bit lower. Why? Because I'm going to draw it here. Okay, here's my beam here. Okay, and the shoe, if you remember, we talked about the shoe of the joist, okay, has to sit on top of the beam, and then this would be elevation 6,000. So the top of this beam has to be lower by the height of the shoe. Now, I can tell you right now, these guys had a shoe of 125 here, okay? I can zoom in. Let me zoom in so you guys can see this, okay? They had a shoe of 125 based on the joist that they required for this span. And if I'm not mistaken, if you go to the joist catalog, I believe the shoe for the joist that we're using, it's only 100. So what you do in that case is, of course, okay, so what you do in that case is you tell the guy, drop this side by 100. So when you want to drop something, you put a minus sign and you put in bracket. That means that the top of this flange will be 100 millimeters below the elevation 6,000, and then this one here. So all of these beams here would be dropped by 100 in your case. This is 125, but like I said, this was a shoe for this joist. And if I'm not mistaken, if you go to the joist catalog, for the size of joist that we had, the manufacturer will tell you the size of the shoe. So the shoes are either 100 or 125. And therefore, in your case, this would be 100, not 125. Now, after that, so what happens here is that here, what they did is they calculated the slope. In other words, they took the furthest distance from this drain here, okay? And then what they did is they calculated, for example, here they had 1250, 1250. And if I'm not mistaken, that would be 25 times 2, that would be 500. So what they did is they dropped the top of the steel right here would be 500 millimeters below 6,000. In other words, that would be at 5,500. And this way, when they put the, and then after that, this would be halfway between the two. So therefore, they would drop this by 250. So what you have to do is you have to create in your steel structure the slopes that the architect's going to need to be able to drain his roof. And then when the fabricator is going to be fabricating your steel, the steel detailer for the manufacturer, he'll keep in mind to prepare all his shop drawings based on the information that you show him here. Okay, so that's okay. So clear, and let me go back. Okay, so that's what you see here that you don't see. And then of course, don't forget, you would have to show where your cantilever is. Okay, remember your cantilever is at 2.5 meters on this side and 2.2 meters on that side. So you have to show your cantilever. Now we'll talk about this. Okay, these are tie joists. In other words, we'll talk about this when we talk about columns. Okay, and in this case here, this person should have used two different symbols. Okay, they put one for a tie joist, and then they use the same symbol for the knee brace. Okay, I would suggest that you come up with another symbol for the knee brace. Okay, and therefore, because when we design these things, we say we're going to laterally brace them, and therefore you should use a different symbol. So your legend, so here they put a plus sign for the tie joist, so the manufacturer will realize, and we'll talk about why we need tie joists when we talk about columns.
Sir?
Yes.
Can I ask a quick question?
Yes.
Because I didn't really understand. So I get it from the minus 125. You're going to go all the way down to a minus 500 for the slope of the roof, right?
That's right.
So
Wait, let's start with the minus 125. What do you understand from that?
it's going to, you're at elevation 6,000. You're going to go minus 125.
But why do I go minus 125 there?
Your joists are going to sit on top of
Exactly,
there.
but you're not going to have minus 125, you're going to have minus 100. So here, when I put my joist sitting on this beam here, they're all, the top of those joists are all going to be at 6,000, all along this line here and all along that line there.
Okay, so the top of joist is at 1,600, but then the top of that
Yeah, because if you don't tell the guy to drop the top of the flange, how are you going to get the top of the joist to be at 6,000?
Yeah, okay. And then so my question is, for the minus 500, it means that from B to C, your joist and everything are going to be going diagonally down.
Which one? From B to C? No, the joists are just going to be, all you're going to do here, you're going to drop this column, you're going to make it half a meter shorter. Okay, that means that the beam here, see that the top of the beam right here, believe it or not, the top of the beam right here is going to be at, the elevation of the top of the beam is going to be at 6,000.
Okay.
And then all of a sudden it's going to drop by, and half a meter within this length. So here the slope's going to be more than 2%. You follow?
Yeah.
But I don't care. I said you need a minimum of 2%. So you want to make sure from the furthest point away, the water can drain down by 2%. So that means that here, by doing that, when they put all these different heights for all the columns here, okay, for the steel, and after that, when they come, excuse me, when they come and put these high, you're going to get all the right slopes in your steel structure, so that when they put the steel deck, you'll actually see the steel deck kind of sloping towards your drain. You follow?
Oh, okay.
You want to make sure that the steel deck has that slope created in it to get to your drain.
Okay, I get that now.
You get that now? Okay.
Yeah.
So you guys are going to have to calculate, for example, like I would suggest you might want to put your drains where these are, or if you want to come up with something, like I said, this is something that's discussed with the architect. Okay. Like he might want to put a drain. He might want to put a drain in each one of these bays. I don't know. It's up to him, you understand, for whatever reason. And then once he decides, because he's got a limit on how big of a basin he's allowed to have on his roof. Okay, so there's architectural constraints, and then he'll tell you what those architectural constraints, and then you have to figure out how are you going to adjust your steel, okay, so that you can create that slope for him so that his roof is going to drain properly. And then from there, the mechanical engineer decides what's the size of the drain required. It's going to be a 4-inch roof drain, it's going to be a 6-inch roof drain, and so on. Okay, and okay, so these are all things that get coordinated between you, the architect, the mechanical engineer. Okay.
Really, the mechanical engineer would say the roof drain.
Yeah,
See
he's the one
how?
that's going to size the roof drain. You're not going to do it. Neither is the architect. It's a plumbing issue.
Ah, true.
So therefore, it's the mechanical engineer that decides. For example, he'll go to the. He knows, for example, based on the amount of precipitation that we have in Montreal, right? In a 15-minute, what will be the flow? And then, you know, like you guys did this, right? You did flow calculations with Mrs. Babruzzi. So you guys should be able to size these things if you want. I know how to size these things. I've done it for myself, but like, because I've taken a hydraulics course just like you guys did. But in theory, if you're doing a project, the mechanical engineer has to worry about that. Is it going to be a 4-inch drain? Is it going to be a 6-inch drain? And so on. Let him worry about it. You understand? And what type of a drain he's going to have and all that. So that's going to be his problem. Now here we next week in the next lab, we're going to be designing these interior columns. Okay. So we'll be doing that next week. So you know what size of columns to specify here. Now, don't worry about these details here. Okay, these are the details that you guys are going to show later on as we develop the project. And of course, here is the general notes, okay, that you need, okay. So here, for example, they instead of, we decided to use a 38mm deck, they had to use a 76 because the spans here were fairly high, and they ended up using a 900mm depth joist, whereas you guys, I think we decided was 650. So this is stuff that you, and then of course, this is the steel that you're going to be using for the W shapes, and then you have to specify the steel for the HSSs, which they didn't do here. Yeah, she did specify the HSSs. I do recommend that when you're specifying your steel, keep them all together, okay? So this is the steel that we're going to be using for the HSSs. This is the steel we're going to be using for the plates and so on. So here, this is where you put your general notes. And of course, you always give your loads because it's the fabricator of the joist and the deck that's going to decide based on what you show here. Okay. And of course, we're going to talk about wind load, and you're going to have to show your wind load. Okay. And then the manufacturer knows how he's going to have to design his joist for what loads. So is there any questions on this drawing? I think it's still fairly, it's fairly clear, but this is the only thing, like I said, the only thing that you guys weren't aware of are these slope lines here, okay, and how to make these calculations. Like I said, you should be able to easily calculate what 2% is, okay? So as a matter of fact, if I'm not mistaken, if the top is steel here, there's a slight mistake here because if the joists are sitting on top of the beam, there should have been minus 500 and then less another 125. So this was a mistake, and I probably picked up on it and I marked it wrong. Okay, so keep that in mind, because the 2% is, for example, what I'm trying to say is that 6,000 is where your steel is. You want the top of that joist to be at, like in her case, or I think it's a she, yeah, Emily, you want it to be at 500. You wanted the top of the joist to be there, and you know that this joist has a shoe of 100, so she should have put minus 600 here. Okay, so that it's the joist that happens to be at the right height, and that was a mistake. So that's a mistake. And of course, that's a mistake also, and they're all wrong. So therefore, she probably lost a couple of marks for that. Not, whatever it was. So now, of course, you have to show the length of your overhangs, because this is very important, because you use these specific lengths to do your analysis. That's very, very important. Okay. And in this case here, they ended up getting fairly bigger beams than you guys. Even the drop-in was fairly bigger. So, okay. And so far, what you guys can do is, of course, you can do about 95% of this drawing. Okay, 95 or maybe 90%, because you can definitely, work out, where your joists go, where your columns go, what your dimensions are, and so on. The only thing that you won't do right now, we've already designed the perimeter beam, so you should be able to put the designation for your perimeter beams. And the only thing we haven't done yet are the interior columns, and of course the exterior columns are very specific, and that's going to be a lab by itself. Okay, so you have this that's going to guide you on what you're going to have to do for your drawings. Now, so that's, and then after that, once you've shown the roof structure, after that you need to show, the elevations. Okay, so in the elevations you show what you have. Okay, so in other words, here this was 6,000, and then of course the girths at every 2,000. This was we're going to be designing these braces. Now, you don't see this on your project, but I expect everybody to put one overhead door, or at least one overhead door somewhere in your elevation. Okay, and I want you to put at least one man door, because you have to have man doors. Okay, so here I told everybody, it says put at least one overhead door in each elevation. Okay, and then these are to frame around the man doors. And if you guys aren't clear about that, when we get to the girths, we'll talk about that. So these here are the elevations. Okay, you always show north, south, east, west. And like I said, we talked about the sag rods, what they're for, and so on. And here she specified what her braces were, the HSSs and so on, the sag rods. And we are going to design the girths after we've designed the columns, because then we'll have the wind loads and we'll be able to design the girths. Okay, so that's going to be it. Then the third drawing you're going to have, and of course we're not there yet, it's going to be towards the end of the semester, you're going to have details. Okay, so the details are going to be the details of, this is the connection between the I believe this is the connection. If you go back to the first drawing, 1C4, I don't know where she did this detail, but if I go back to drawing number 4, so this is the detail here for that. And then, so this is how she indicated where these details. So 4C4 is for the connection between the drop-in beam or the suspended beam with the your Gerber system, and then this the one to the column. And we're going to learn how to do this. The only thing that you're going to learn how to do these connections in class. Okay, this is the only one that, because it's an eccentric one, I'm going to show you how to do this in the lab. So you're going to have to be able to do those. This thing's in the way. So these are the details. Okay. Okay. So this is the detail of connecting the drop-in beam within your Gerber system. Okay. And I'm going to show you how to calculate what size you need this. So this, because this is an eccentrically loaded connection, I will show you how to do that. And of course, we'll talk about this when we get to connections. These are cooped beams. In other words, you cut out the bottom of the beam so that you can drop it in. When you're erecting, you're able to drop it in between these two angles properly. And that's why we coop the bottom of the beam. Okay, and now you know why we take 80% of VR in the tables, because if we need to do this, this is what we remove from the web. We remove also the areas of the holes, and that's for, you want to compensate to make sure that your VR value here is greater than your VF value. So you're starting to understand why we take 80%, as a minimum VR value when we go to the beam selection table. So, and then after that, the rest is basically more details, and these details will be developing as we learn how to do them. Okay, so in other words, here's some more details. I'll show you how to calculate. We're going to calculate the force that comes into this brace, and then we're going to be able to calculate the connection. So this is the connection of the brace at the base plate. This connection of the brace at the top plate. This is your base plates. We are going to be starting to design these next week. This is the base plate for the interior columns, and the exterior columns are very, very special because of the wind. They have what we call an eccentric loading, and I will prepare for you, like I did. Whenever something is outside the scope of this course, I prepare you an Excel sheet, and I'll show you with the Excel sheet how we can calculate the thickness for eccentrically loaded base plates. So those are the 4 drawings you're going to need to put together. Now, what I did for you, okay, the next one's going to take a little bit longer to come together. It's going to open up. This is an AutoCAD. Okay, so I have to open up the whole AutoCAD. My whole AutoCAD program has to open up. Does anybody have any questions while we're just waiting for this thing to open up?
So let's say in the March break, what can we do?
You can do 90% of your roof plan. You can do 90% of your elevations. And the only thing that you can't do are the details. You understand?
Okay.
You can probably do your base plates, because I think next week we're going to be doing base plates. I don't have the schedule on the top of my head. But you can put in all the designations of your beams on your roof plans. I think we already did all the perimeter beams. We already did all the Gerber ones. We'll have the interior columns done next week. We'll have the base plates done next week. And so, I mean, like, you can do quite a bit. The only thing that you can do is a lot of the details that are shown on drawing 3 and 4. But if you get half your drawings done by the March break, like 90% of both of them done by March break, wow, you know, that's going to be great. For some reason, my AutoCAD is taking a while. I apologize. Like I said, it's yeah. Now, I think I simplified your life a bit with the template, and that's why I want to show it to you. So this way you guys won't panic. And where is the... I guess it's still opening up. Huh? I should have maybe opened up AutoCAD, and then I could have just opened up the drawing, but I apologize for that. Okay. Oh, there you go. Does everybody see the AutoCAD drawing?
Yes.
Okay, so let me close this. Let me maximize this. Okay, so what I've done here, guys, believe it or not, okay, I've really simplified your life, okay? Believe it or not, guess what I did? These grids are spaced for your project. How's that? And these columns are for whatever, you understand? So basically, all you have to do here is, of course, okay, you're gonna, you know, start from here. You understand? Like, in other words, I always like, for example, I like to work in layers. When you're working in steel, okay, your columns, if I'm not mistaken, let me go to home here. I have a layer called columns. Okay, so when you're doing columns, make sure you're on columns. Okay, so here it's very simple. You know, you simply copy those across there, you copy, and then take those and you copy them down here, and then you take these two and you copy them there, and then you take this one and you just copy. So you copy all your columns wherever they are. After that, you start drawing your lines for your, you draw this line here, you draw this line here, and then you, of course, you put in the lines for your joist. Remember, the lines are not supposed to touch in structural steel. So look at the other drawing. If I see lines that touch, you're going to lose a lot of marks, because in structural steel, when things are pin connected, in other words, simply supported, you have to show them that they're not touching each other. That's how it's represented. Okay, so this is it. So this is your drawing to do your roof plan. And then what I also did for you is I did one so you can start your elevations here. Okay, so here you go. I even set up all the things for you so then you can start doing your elevations. And believe it or not, this is for your details. Okay, so people say, well, how come they're so small? Because here you're going to be working at 1 to 10. So in here, you're going to be working at 1 to 10, okay? So you're going to be drawing at 1 to 10, and then when you're going to be plotting, you're going to be plotting at 1 to 20, 1 to 10, and then when you're going to be, if you need to dimension something here, this is how I work with AutoCAD. I work, this is my 1 to 10 drawing, so therefore when I come to annotate, I have one, this is for the 1 to 200 scale, and then when I want to annotate to 1 to 10, I come here, and that's 1 to 10. So for example, if I, you know, like just to show you the difference between the two, and therefore I go to 1 to 10, and then AutoCAD will automatically do the calculation so it shows the right dimension. Okay, so that's how I basically do it. And here you go. So here are all your connections, and then of course these numbers you're going to show them on your plan, and that's where you're going to be doing your drawing. So this is going to be one sheet for one detail, and that's the other sheet for the other detail. So for example, if I happen to have draw a line. Let me just go draw a line. I'm going to do this here. Okay, draw, for example, if I draw a line that's supposed to be 600, oh, I better put this on ortho. I don't know, 600. Okay, and so on. And I'm drawing my detail here, right? So if I want to, okay, so when you're ready to, when you're ready, sorry, when you're, oh shoot. So if I do linear, okay. So this is for your details, okay? And that's it. And then when you're ready to plot, it's just like you would do the other thing. It's like you do the same thing, you would plot. The only thing is that the same size of paper. The only thing that you put a scale of 1 to 10. So if I plot this on the same size paper, and I think I tell you what the paper size is, the same size of paper that we have for the size of paper is 11 by 17. So for example, if I want to plot this here, I do the same thing I did before. I simply say plot, and of course, okay, so that it's not there. So in other words, you're gonna plot it as a PDF, and then of course 11 by 17, the full bleed, that's the size of the paper. You're gonna pick a window, and of course you can go from there to there, and of course now you want to center it. This is a 1 to 10 scale. Okay, so you don't want to fit it. Monochrome, you want to do a preview. You do a preview, and there you go. It would fit perfectly on 11 by 17. Okay, and the other one is exactly the same thing. Exit. If I do cancel, and if I do the other one here, it's the same thing. When I'm ready to plot this, plot. Where's plot? There's plot. Okay. This is the AutoCAD PDF. And then if you were at school, you would have picked the printer that's in the lab. And of course you pick a window. I'm going to go from here to here. And now of course I'm going to change the scale 1 to 200. That's the scale of my drawing. Oh, it's not here. So therefore I'm going to put custom 1 to 200. That's what it is. And so on. And I do preview. And there you go. That's exactly 1 to 200. So when this thing would come out of the printer, you take your scale 1 to 200 and everything would be to scale. Okay. Now, do you guys want to know how to do this on your own? How you set up your template so that you can always make sure your drawing ends up on your sheet size, or you're not interested?
No, we're interested.
You're interested? Okay. Guys, whenever you're plotting anything in AutoCAD, okay, it's very simple. I mean, exit. Okay. Okay, cancel. Okay. Whenever you're plotting anything in AutoCAD, right? Like the first thing you need to worry about is, okay, what are you going to be plotting with, right? Of course, if at home you have a printer, you have a small printer, you would have your printer set up here, right? And most likely on your printer, you only have, you can probably print maximum 11.5, 8 by 11, 11.5, 8.5 by 11. In other words, an A size sheet, right? Now, I want to show you that, for example, this is the paper size. Okay, so these are all the paper size that you can have, right? In other words, A size, B size, and so on. If you're doing it in imperial, okay. Let's do this one in it makes no difference. I'm going to do this one in metric, and therefore you guys can get to know metric. Okay, so if I pick 17 by 11, okay, if I hover over here, this is the paper size. Okay, now be careful because depending on how you orient it, the printable area is going to be different. So this is the paper size, but this is what the program is actually going to be printing on, that printable area. Okay, so now if I change this, for example, if I change this to inches, to millimeters, it's going to tell me what the printable area is in millimeters. So right now, that printable area in millimeters is 419 by 241. okay? 419 by 241. So if I want to plot something on here at a 1 to 200 scale, I know that for every millimeter of paper that I have, I can put 200 millimeters of 200 drawing units or 200 millimeters of drawing units, okay? So I would take the 491 multiplied by 200, and I would take the 2, whatever it is, the 241 multiplied by 200, and that would give me how big I would make my border. And once I've established that border with the command there, with the rectangle, as long as I stay within that border, when I'm ready to plot at 1 to 200 on this paper size, it will always fit. So for example, if I would be doing this now, like for example, I got here, I'll do the math, okay? I got 419 by 241, and I want to plot this 1 to 200 one day. So I'm going to say 419 times 200. For every millimeter of paper space, I'm going to be putting 200 drawing units. And in this case, the drawing units are in millimeters. I got 83,800, and 241 times 200, that's 48,200. Okay, so basically, okay, I'm going to cancel this. Okay, so if I come here, for example, and I say here, I'm going to draw here, and I'm going to go out by 4, what was it, 8, we said 83800, comma, 48200. Now, there is the virtual space that I'm limited to. So now when I'm ready to plot this, I say plot, okay? And that's the paper I want to plot it to, and that's the size I want to plot it to. And if I pick, and I say pick a window, and I go from here to here, and everything's set, and I do custom monochrome.
You have to choose the printer.
Oh yeah, I have to choose a PDF. Okay, PDF. And this doesn't matter, PDF. Okay, printer, I do a preview. And look at that, it fits on my sheet. You see, so that border that I created will limit the virtual space that I have in front of me to say that if I stay within this boundary, when I'm ready to plot on this piece of paper, it will fit at the scale that I want it to. So at home, if you have 8.5 by 11, you go find out what the printable area is for your printer. And then all of a sudden you create your limits, what I call your limits. In other words, you create your border. If you want to draw, for example, 8.5 by 11, if we do it, like let's say you guys are going to do this at home, okay? So let's cancel this. And you want to print to scale on 8.5 by 11. So you want to print at home 8.5 by 11. So very simple. I'm going to say print, okay. And again, we need to take the AutoCAD PDF, okay. Now I'm going to take an 8.5 by 11. Let me go, that should be 8.5, should be 8.5 by 11. So this is what you guys should have at home in terms of, or you can take an expanded A, whatever you want to take, okay, whatever you want to take, 8.5 by 11. Now, what you want to do is you hover over here, and this is 10.61 inches by 7.71 inches. So that's if you want to do it landscape. If you do it portrait, the printable area is slightly different. So you decide which way you want to do it, okay? Now, if I'm drawing at 1/4 inch is equal to a foot, right? That means that I can literally multiply that value by 4. That means in every 1 inch of paper space, I'll be able to put 4 feet of drawing units. Therefore, I would make it 10, I would say 10.6 times 4. That will be 42 feet in one direction, and then 7.7 times 4, and I would make it 30 feet in the other direction. And once I draw that triangle, if I make sure that my drawing stays within that that rectangle of 42 feet by 30 feet or 30, okay? If I make, and then when I'm ready to go plot on my paper at home and I put a 1/4 inch scale, it will fit, okay? And then of course, what you have to do is if you're starting your drawing, okay, if you're starting your drawing, and then when you're starting to do your dimensions, if you want to make sure that your dimensions, sorry, cancel. If you want to make sure that your dimensions come out nicely when you're drawing it, you have to tweak one little thing in the dimension style. So in the annotate, okay, so here, for example, let's say this was the one, the standard one, modify, okay. You'll notice that here where it says fit, I have an overall scale factor, okay. So if you're plotting at 1/4 of an inch to a foot, that should be 48. If you're plotting, understand, this is where you have to put this in here so that all the default values in AutoCAD get adjusted to that paper scale that you want to eventually get to, okay? And that's where you tweak that number there, okay? And that's going to adjust all your arrowheads, all your dimension lines, all your text size. That's what it is here. So depending on what you're doing. And if you notice, like here, this is for the 1 in 200. And if I went, okay, and I'll show you what, and then when I went to 1 to 10 to get the same, always the same arrowheads and everything else, I simply went in here and I did 1/10 of that size. And then all my arrowheads were the right sizes. And that's, guys, like I said, I've been teaching AutoCAD like this since the very beginning. I know that you can simply do everything in model space and then drag everything into paper space and get the templates and then hope for the best. And I've been hearing a lot of complaints from students saying we always have a problem fitting our drawing onto the paper. Am I correct?
Yes, sir.
You see? So by you dictating at the very beginning what your limits are based on that printable area, you'll never have that problem. And that's why I believe that we should be able to know what we are limited to and work within those confinements, and not all of a sudden after the fact say, well, let's just fit the drawing to the paper and let's go on. Because that is the worst thing you can do, is not send a drawing that says scale 1 to 200 and it's not scaled to 1 to 200. You understand? It can be a problem, especially for the estimators, if they're using their scale to do the estimates off your drawings. You understand? Okay, so that's all I want to say today. So I hope you guys, so like I said, this is for your two, like, and then these two little drawings here are for your details. So everything's set. You just have to go in there, and like I said, this you'll probably be able to start doing 2-3 weeks from now when we get into the details, but you can't easily do this drawing here. And guys, like I said, when you're doing AutoCAD, please do yourself a favor. Okay, do yourself a favor. Okay, remember what is, remember what is typical. Okay, so therefore, for example, when you say the copy, okay, I'm gonna, and so I copy, oops, sorry. I forgot to go perpendicular. I did nearest. I wasn't paying attention, so I'm gonna have to erase, okay? And then after that, now what I like to do, okay, and then of course, since this is the same as down there, I simply say copy again. I love the, understand? And okay, and then you copy these two and so on. So, and then after that, when you come in here, okay, and once you've created a typical bay in here, then just copy it all the way across, you understand? And then once you copied all the bays here, they're all going to be the same. Copy it all the way down. Remember here that when you're ready to do your beams, so you first worry about doing all your columns, and then you change to objects for your beams. So because the lines, the column should be the heaviest line in the structural steel, because those are the predominant elements in your structural steel. Then after that, you go to change your layers and you draw a line. So for example, from here, you draw a line, okay, whatever, and make sure that, okay, now like I said, make sure that this line doesn't touch, so you can simply, you can drag it back. And if you're going to drag it back, be consistent. If you're going to drag it back by 100, make sure you put 100 all over, okay? 100 is not very much. That should, at this scale, is not very much, but at least it's not touching, okay? And of course here, I don't remember what the cantilever was, but this line should not be further than the cantilever here, okay? And then, you know, and then of course, once you've done all your beams on this side, you simply take them, you copy them with the columns, and you just put them on here. So you work on this, and then you copy them down here. So this way, it's all done. Understand? And then you start putting in your joists and so on. And then as soon as one is ready, I mean, if this thing was pretty much symmetric, I would even use the array command to be able to put in all the joists if I wanted to. But it's up to you. I find by doing one copy, 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 it might take you 30 seconds longer than using the array, and it's up to you. So look, guys, look for repetitiveness, okay? And AutoCAD is a program that will execute your command. And the way that you master AutoCAD is realizing what is the least amount of commands I need to be able to achieve my drawing objective. And that's what, and if you manage to do that efficiently, you have mastered AutoCAD, okay? And that's why, like, for example, for me, the nice thing about AutoCAD is that if I can find symmetry, I only have to draw half. If I find 2 lines of symmetry, I only have to draw a quarter. So I always look for symmetry. Once I find no symmetry, like for example, if this thing was symmetric here, you can literally, this thing is symmetric. So if you want, you can only draw a quarter of it, and then you can mirror it, and it's all done. It's up to you. Do what you want. All I'm saying is that at the end of the day, the faster you can draw with AutoCAD, the easier you are going to make your life. And of course, if you're actually doing it on a stage, the more they'll pay you for your drawing capacities. So that's all I
Sir,
can tell you. Yes.
are these columns though? So we just put columns without their like actual sizes because
In structural steel, when it comes to the columns, they're shown graphically. You don't put the size of the column. Okay.
okay.
I
And
know
that's
that
on beat then.
Rivet will put the actual size because that's how the program works. Okay. But in structural steel, the column sizes are shown graphically, as long as they're not too big and as long as they're not too small. In other words, they have to be able to read easily on the drawing. And if you look at the size of the columns I have here, they seem to be able to read properly at this scale. What do you think?
Yeah, they do. Okay.
Okay. So that's what you have to keep in mind. So, and like I said, so I know that Rivet will actually put the actual size of the column inside your, you know, in your model, which is that's how the program works, you understand? But in reality, when it comes to structural steel, the column sizes, like for example, this represents a beam. Do I show the actual beam size? You understand? So structural steel drawings are they're like stick drawings mostly. You understand? They're all sticks. You know, line here, line there, line there. You understand? But there are certain graphic rules, like here, that this line doesn't touch. Okay. And that means that, and then this goes over it. So therefore, that means that the column is below the beam here. These are all little things that are significant in structural steel. Okay. So here, for example, the beam, like I said, this should be the minimum distance you should leave. Okay. So if I come here and I draw a line here, okay, from here to there, and then of course, now some people like to sorry, I made that a little too long. I apologize for that. Let me drag that back. Okay. Now, like I said, my graphics card is, okay. That's not where I want it. And it still doesn't go where I want it. There we go. Now, in the old days, guys, before we had these drag points, now AutoCAD, of course, the newer versions, right? In the old days, before we had these drag points, like people would have to like draw a line, trim the line, and be able, like what I used to do in the old days, instead of doing that, I used to use a scale command. This is me in the old days, okay? I would take my scale command, I would take this, find the midpoint, there's the midpoint, and then put something less than 1.95, you understand? And there you go. And that's how I'd be able to trim that line. That's manipulating the command to do what I want with it, you understand? And if I found that to be a little too much, I would just modify my scale ratio, you understand? And then once I got that to where I wanted, of course, I would just have to copy, and so on, okay? So guys, like I said, AutoCAD is fun. I mean, the more you know how the command works, the more you can learn how to use it. People say, well, these are tricks. They're not tricks. It's just understanding what the command can do for you and understanding how you can apply it to get the result that you want in terms of drawing. And guys, don't get discouraged, because you are also learning how to draw at the same time. So not only are you have the hurdle of using a drawing program that you need to get used to, you also have to develop the drawing, your drawing capacities simultaneously. So your task is twice as hard as mine. You understand? See, like when I went to AutoCAD, I was drawing manually. So I already knew how a drawing was supposed to come together, and I could be able to visualize what the drawing is supposed to look like. So therefore, all I had to do was learn how to use AutoCAD to replace my manual drawing techniques. But now you guys are learning both simultaneously, and with time, it's like anything, time, you will start mastering both, and it will become easier. So don't get discouraged. It's very, very doable. I mean, once you get old and gray like me, you'll definitely be able to do it. Fair enough. But hopefully, by the time you get there, you'll have had a nice career, and you'll have enjoyed yourself, you know?
Sir?
Yes.
I just want to check something.
Okay.
About the project. When we, I understand we have to submit this file, but for the let's say for the design, the 2 steps before this, for the perimeter beam and the girders, we have to show you the ADA, and we have to show you we don't have to show you the Excel, just the ADA, like the
Well, I mean, you're gonna have to show me. You're gonna have to show me your ADA results, and then you're gonna have to show me like that you took the results from ADA and you put into the Excel sheet, and that it worked. Understand?
I mean, like we have to copy the Excel sheet and like show you that.
Yeah, I want you to insert like a copy of your Excel,
Okay.
print it as a PDF, and put it and throw it in. You understand?
Yeah.
Okay, so don't worry. At the end, like near the, like just okay. I noticed that you know, like one thing I like about Leah, the distribution, it tells me who's doing what, and I can tell you some people haven't even opened up the Excel file, so I know they're not doing it. They're not keeping up with the project. It's not my loss, okay, guys. I don't know if I told you this, but if I find somebody copied off somebody else, you both get 0. Not the person I copy gets 0, you both get 0. So you're taking a risk helping your friend out. You can show them how to do it, but don't, if you let them copy blindly, if, for example, when I go through this, for example, I'm very good at AutoCAD, and I'm very good at picking up people that copy and not doing their work. So if you can take the risk, you might be able to slip it by, but if I catch somebody copying, wherever he copied off, or wherever the person offered him to copy off, you both get 0. And you get 0, that's it. You get 0 for the project, and you get 0 for your what you call a comprehensive assessment. You will not graduate. Okay, and that means that next year you have to come back and finish your steel project. So do yourself a favor. Don't copy. If I catch somebody copying, it's an automatic 0 for the person that copied and the person that allowed him to copy. So both people are at risk. Okay. So keep that in mind, guys. Okay. You know, I encourage you guys to work together, share, you know, help each other. I'm not too crazy about these lines. Hold on a second. LTSCALE, LT scale. That didn't work. That's better. Okay, the LT scale was slightly off. 4,000. That's good. Okay, so guys, keep that in mind. Okay, so the guys that are just, you know, like aren't keeping up with the workload, and then at the end, they're hopefully going to copy one off their friends. It's up to you. Take the risk, you know, or let it all pile up at the end and then do haphazard job. And if I find that the job's not well done, you know, I'll give you what you deserve. Trust me. Okay, I will reward the people that are working, and I will punish the ones that aren't. So, and I'm here to help you all the way. So I need you guys to do your part. I can't do that for you. I can only guide you so much, and then after that, I leave it up to you. Okay. So there is your. Okay, so I hope you appreciate that I set up this template for those that want to do with AutoCAD. Okay, the ones that want to do it in Rivet, by all means, go ahead, use Rivet. I don't care. I find that steel and rivet is very, very, very friendly. It's up to you. Okay.
All right, sir. Another question for the when we do the perimeter, we have to show you the what's it called, the deflection.
Yeah, in other
And
words, once you've selected your beam, you know that that's the size that works. You put it back, you put that designation in your ADA, right?
yeah,
And then you just put the snow load on as a load case without any factor, and then you show me what the deflection is for that beam.
okay, for both of them, the long and the short.
Yeah, of
beam,
course.
basically.
Yeah,
Okay.
yeah, of course. Like on the long side and on the short side. Yeah, because you have two beams there. You understand?
Yeah, yeah.
Sounds good.
Sounds good. Yeah.
Like it's like it's not very, very complicated, but like it's.
I'm just writing notes. I'm just so I don't forget.
No, I'm good. Good. Like I said, that's and that's what's nice about ADA is that once you size your beam, you can simply take that designation, the size that you get, put it back, put the right size in your model, run the analysis, and don't just use. That's why we don't factor our loads in ADA. We put all our specified loads, and then it's the load factors that will give us our design loads. And by putting one, we just use our specified loads for deflections, and it gets all done. Is there any questions here regarding the template? Is everybody clear with that? Because I'm going to close this and I'm not going to. Okay, so let me. No, I don't want to save these things. Okay, I'm going to put this on the recording on